Another application of the integral is found in physics, and for those who haven't taken physics, it's not that much of an issue. You can probably just get enough from the video I'm going to show here. But there's a term in physics called work, which occurs when force is moved, or force is used to move a body a certain distance. So as long as your force is constant, then you don't need calculus. You just have an equation, force times distance. But if we were to graph that, where our y-axis was force and our x-axis was distance, then all we're saying is that when you do force times distance, you're getting, so there's a constant force. Right, that's work. That area represents work. And so, similarly to our analogy with velocity, if your velocity is constant, we know that your total distance traveled, or change in position rather, is just the area between the x-axis and the function. And that's not going to depend on what your function's doing. So whether it's constant or not, it's still going to be that area. And so, in general, work done by a continuous force directed along the x-axis. So we're just going to kind of assume that the work is done in this direction. So this x-axis represents distance, really. So you move this object from point A to point B. And your y-axis is f of x. All we're saying is that work is just this area. So you got a force function that's continuous, and if you integrate, you get work. So we'll look at a few examples of this on the next few slides. So here we're told a mountain climber is about to haul up a 50-meter length of hanging rope. And we're asked how much work it will take if each meter of rope weighs 0.74 newtons. So often force is described in using the units newtons. So that's our force quantity. And so what you want to imagine is that, somebody's pulling a rope, kind of a pathetic drawing, but he's pulling a rope. It's a 50-meter rope, and he's, as he pulls the rope up, it gets lighter, right? So it's heaviest for him right at the very instant he starts pulling it. And we know that it weighs 0.74 newtons per meter. So I usually like to graph the situation just so I can see the area I'm going to be summing. So I would do something like this. I'd say, well, let's call this the force, and this would be the distance. So we know that he's moving at a distance from 0 to 50 meters. Now, how heavy is the rope at the very beginning? How much force is he required to use at the very beginning? Well, it's 50 meters, and it's 0.74 newtons per meter. So right at this instant, we're going to say that 0.74 times 50, that gives me 37. So again, it's newtons per meter times meters, that's newtons. So at the very beginning of this situation, it's 37 newtons. And it's not 37 newtons the whole time, because as he pulls the rope up, it's getting lighter. And it's getting lighter linearly, since every meter he pulls up is going to decrease the weight, or the force rather, by 0.74 newtons. So by the time it gets to the 50, it should be 0, and that should be a linear change. And so we're interested in this area here. That's the work. So you've got two options. One is to use an integral, or not use an integral, use a function for this. So if you wanted a function for this guy here, you could call the function f of x, it's a line with a y-intercept of 37 and a slope of negative 37 over 50, which is negative 0.74. So you could say it's negative 0.74 x plus 37. So you could integrate that from 0 to 50, our distance, and you can put that in here. And so you can use your calculator or the fundamental theorem and get an antiderivative. It's a little bit of an annoying antiderivative to get because of that fraction. But you could also just go back to geometry, right? We're looking at a triangle, and if we want its area, I'm just going to use geometry. It's 1/2 the base, 50, times the height, 37. So that's 25 times 37, which is 925. So let's pay attention to what the units would be. This here, right, that's a force, so that's the units there are newtons, and we're moving it over a distance, so the units are Newton meters, and that is a unit rather for work. All right, so here's a simple example of how you can use integrals to analyze functions or force functions and figure out the total work that was required in a given situation.